Hi, how you all doing? You ready for this? This is differentiation, okay? I've been looking forward to this for a long time, okay? I've really been looking forward to it. Why is it such an important and such a lovable topic, okay? Well, it epitomises A-level maths, okay? It epitomises A-level maths because before that you've been doing GCSE work and you might have been doing graph sketching, yes. You might have been doing stuff with tangents and gradients, yes. You've done trigonometry, done the algebra, you've maybe touched upon differentiation, but you've not really got to the heart of it, okay? A-level mathematics really gets to the heart of differentiation. And then after that is integration as well. And together the two make calculus, okay? And calculus really is the embodiment of what A-level mathematics represents, okay? There's a lot of really cool stuff that you're going to see, and you'll see it not just in pure mathematics, but you'll see that in mechanics as well, in the applied mathematics, okay? And there's a lot of challenging questions that can be done with both differentiation and integration. And it's a very glamorous topic as well, okay? You've got the whole Newton-Leibniz battle, who came up with it first, and yeah, it's one of the most major important discoveries of mathematics, some say in all time as well. It's a major game changer, okay, in terms of what we were able to do as a species once we'd actually discovered calculus, okay? So yeah, lots of reasons to get excited about what differentiation holds in store for us, okay? Right, what I'm going to do today is kind of introduce it for you, and I'm going to pitch it at a level that's easy for anybody with some mathematical knowledge to understand. So you're probably an A-level student watching this, but you could also be a GCSE student, you could be a year 8 or a year 9 student, okay? So I'm going to kind of pitch it at a level that is kind of easy for people to understand. And if you are a year 8 or year 9 student, yeah, sorry, you have to wait a few years before you actually get into differentiation, but thanks for watching the video, okay? Or maybe you're just doing GCSE further maths, okay, and you want to sort of see this, how this is going to pan out for you, okay? Well, what I'm going to do is I'm going to start with a well-known curve, okay? So the graph y equals x squared. And differentiation, where you can look at it from the point of view, is about trying to find the gradient at a particular point on a graph, okay? Now, with straight lines, it's pretty easy, all right? You do that quite easily enough, I hope, at GCSE level. But when you've got a curve, finding the gradient is a bit harder, because the thing is, as you move along the curve from left to right, the gradient is always changing, okay? The gradient, remember, measures the steepness of a curve. It's how steep a curve is at a particular point. On a straight line, it's the same steepness all the way along, okay? So it's pretty easy, but the curve is different. So it might be the case, for example, that I want to find the steepness of that curve there. All right. Now what we can do is we can draw a tangent at that point, which of course is a straight line, and that tangent represents the steepness of that curve at that point. So the gradient of this tangent will be exactly the same as the gradient at this point there, okay? But suppose I choose a different point here, okay, and I draw another tangent like that. Can you see the gradient has changed, okay? And it's the case that when I choose different points all the way along this curve, the gradient is always going to be changing, okay? What I'm going to do is I'm going to use my pen to represent the tangent, okay? So as I move along the curve, okay, can you see, because the pen, represented as a straight line, is getting steeper, the tangent is getting steeper, and so the gradient is actually increasing, okay, all the way along the curve, all right? And that's where differentiation comes in, okay? Differentiation enables us to come up with a quick method of being able to find what the gradient at any point in the curve is, okay? But what I'm going to do is I'm going to slow it right down for you, and I'm going to just concentrate on what is the gradient at this particular point here. Let me just draw this again so it's a bit clearer. Now, to make things simple, I'm going to start off with a straightforward coordinate point on the curve, okay? I'm going to say that that's got coordinates 2, 4, okay? So if the x coordinate is 2, the y coordinate, x squared, 2 squared is 4. And I want to work out what the gradient to that point is. Now, one way of doing it as an estimate is you draw the graph, plot it accurately on proper graph paper, and then you use a ruler to draw a tangent as accurate as you possibly can, and then choose 2 points that lie on the tangent, and then work out the gradient between those 2 points. That's one way of doing it, okay? The disadvantage of that is it's not going to be accurate, really, is it? Okay? It might be a little bit accurate, it's not going to be 100% accurate, okay? And mathematicians need 100% accuracy, okay? It's what we're here for, it's what we strive for, okay? We want 100% accuracy, 100% perfection. Okay? And the method I'm about to talk you through is going to give us that. Okay? Now, before we go for the 100% accurate method, okay, let's just look at how we might approximate the gradient of this tangent. Okay? Now, the first drawback is, as I said, drawing the line with 100% accuracy, never going to happen. Okay? So what I'm going to do instead is I'm going to choose another point that lies on the curve. All right? I'm going to choose a point that's fairly close to that. So I'm going to choose the point with coordinates 3, 9. Okay, so when x is 3, the y coordinate is 3 squared, which is 9. So I've just chosen the next integer point along in terms of the x coordinates. Okay, and what I could do is, instead of working out the gradient of the tangent, I could work out the gradient of the chord joining those 2 points together. Okay, so the gradient of that chord, I'm going to call that point A, and I'm going to call that point B1, because I'm going to look at further points afterwards. Okay, and I'm going to work out the gradient of that chord AB1, which is pretty easy. Okay, because of course it's just a straight line. All right, so let's work out the gradient of that. So difference in y coordinates, 9 subtract 4, that's 5. Okay, and difference in x coordinates, 3 subtract 2, that's 1. Okay, so 5 over 1, that's just 5. Okay, right, what I'm going to do next is I'm going to look at a point that's even closer. Okay, I'll get much, much closer. All right, so if I get a point that's closer there, I'll work out the gradient of this chord, like that. Okay, and I'll work out what that gradient is, and then I'm going to do it again, even closer, and again, even closer. Can you see what's happening? Okay, what's happening? Look, let me just draw another sketch. Okay, if I just tell you what, if I zoom in on that graph, if you don't mind me doing this, okay, if I just zoom in and make it a bit curvier, so that's the first chord I've got there, and then this is the second chord there, next chord there, next chord there, next chord there. Can you see what's happening? Each time I get a point that is closer to where I'm starting from, the gradient of the chord is getting closer and closer to the actual tangent. That's what's going on. Okay. So what I'm going to do is, okay, I'm going to recognise that actually 3, 9 was not really that accurate. So instead I'm going to go for something really close to the point 2, 4, which is the coordinate 2.1. Okay, x coordinate 2.1. If I work out the y coordinate, that would be 4.41. Check if you want, 2.21 squared, 4.41. Okay, so I'm going to call that AB2. I better call it AB2 because it's the second coordinate point I've chosen. Okay, so the gradient of AB2, so y coordinate change is going to be 4.41 subtract 4, so that's 0.41, and then x coordinate change 2.1 subtract 2, 0.1, and then 0.41 divided by a tenth is 4.1. Okay, so before I had a gradient of 5, now I've got a gradient of 4.1. That's going to be closer to the actual tangent. Okay, now I'm going to choose another point that's even closer still. So let's just put it there. Okay, use your imagination with this one, please. Okay, I'm going to call that coordinate 2.01. I said use your imagination. I can't do a scale diagram, otherwise it's going to be all the way down there. You're not really going to see it. Okay, but I'm going to choose next coordinate that's very close, that 2.01. Now you can do 2.01 squared. You know, so let's do it together. Okay, I know what the answer is, but let's just do it together so that you've got time to understand what's going on. So 2.01 squared, work out that's 4.0401. Okay, and we're next going to work out the gradient of that chord there, AB3, changing y coordinates, these ones, changing y coordinates, so that subtract 4, so of course it's 0.0401 divided by changing x coordinates, 0.01, so that's 100th, that divided by that, again type in your calculator, but you're going to get 4.01. We're going to do one more, okay, so I'm going to call this point B4. I'm going to get much closer now, okay, so the x coordinate 2.001, and again you can do this with me if you want, okay, square that, you're going to get 4.004001. That's a lovely pattern, isn't it? 4.41, 4.0401, 4.004001. So if I have to do it again with 2.0001, I'm sure you can predict it'll be 4.00040001, yeah, and so on. What you've done is you just looked for a pattern there, haven't you? And you just thought, well, I can see the pattern, it's going to be this. This is what this is heading towards as well, okay? We're trying to find a pattern, we're trying to see what's going on. And to be honest, mathematicians are pattern searchers. We're looking for patterns in, well, pretty much everything in everyday life, okay? We want to see why and how things work. And for that we observe, we analyse, we record our findings, okay? We look for a pattern. When we see a pattern, we then think, right, well, let's make a conjecture. We think this is going to happen. And then we try and prove that for all possible values, and then that becomes a theorem, okay? And that's kind of what's happening here. So let's just work out the gradient of that one. Can you do that for me? If you want, just pause the video, or just do it at the same time as me, and just check your answer afterwards. So we could do difference in y coordinates, so that subtract that. So that's 0.004001 divided by difference in x coordinates, which is 1,000th, 0.001, and that divided by 1,000th is going to be 4.001. So look, can you see? Okay, I started off with gradient 5, which is just not really that accurate, really. But then, as I'm getting closer and closer, can you see what this gradient is heading towards? Now the question is, if I were to choose a point that is infinitely close to that, can you imagine what that means? Infinitely close to that, okay? So close that it's actually on the point itself. What will the gradient be? What is these sets of numbers heading towards? Okay, it's heading towards the number 4. Okay, so that's kind of what we're going to surmise, what we're going to conjecture, and it's actually right. Okay, it's actually right. The gradient is actually 4. Okay, what I'm going to do is I'm going to write that here. Okay, and maybe just make a record of that. So on the graph, y equals x squared for the x coordinate of 2. The gradient is 4. I'm just going to make a note of that because I'm going to come back to that a little bit later on. Okay, so all of that hard work just to find the gradient at one single point. Okay, I'm hoping that you found that useful. Right, I'm going to rub the board and we're going to do the same process all over again. Okay, same process all over again. So let's just rub out all of this. Because my diagram's a bit messy now, I'm going to rub out the whole thing and just re-sketch it. Okay, so here we go. Just draw the x-axis and then the parabola. I'm going to use the same graph, y equals x squared, but this time I'm going to choose a coordinate 3, 9. Okay, and I'm going to try and find what the gradient at the point 3, 9 is. So I'm looking for the gradient of that tangent. I'll go through the same process all over again. Okay, so I'm going to call that A. And I'm going to call this point B1. I'm going to call that coordinate 3.1. And of course you've got to work out 3.1 squared is. So it's 9.61. Okay. And let's work out the gradient of that. Okay. So gradient of AB1. Okay. So that subtract that, which is 0.61, and then that subtract that, which is 0.1. And the gradient is 6.1. Okay, so my first estimate of the gradient of this is 6.1. Remember what we're doing here, just a quick reminder. So I've worked out the gradient of that chord. Okay, next job is to find a point that's closer to the point 3,9. So then we find the gradient of this chord. Okay, and the point closer that I'm going to choose is 3.01. Okay, calculator time maybe, even though you can probably predict what's going to happen when I square that. Okay, yeah. 9.0601. Lovely pattern in there, but we haven't got time to investigate that one. And then we work out the gradient of that. So the gradient of AB2 is going to be that subtract that, which is 0.0601 divided by the difference between these two, 0.01, and that's going to be 6.01. Do I need to keep on going? Okay, can you see what's going to happen? If I went for another point, okay, AB3, okay, put it there, and you can visually see, I hope, that the gradient of the chord is getting closer and closer to the gradient of the actual tangent as we get closer and closer. So if I went for B3 and call that 3.001, and you know it's going to be 9.006001 because of the pattern, okay? But then if I worked out the gradient of that chord, can you predict what it's going to be? 6.001. And can you see what this is getting closer and closer towards? Yes, it's getting close to number 6, isn't it? Okay, so I'm just going to save myself a bit of time there. If you don't mind, let's go write that in. So the x coordinate is 3, gives us a gradient of 6. Okay, what's the next stage? The next stage is find the next point along the x-axis in terms of looking at positive integers. Why am I choosing integers? Because it's easier, to be honest. Okay, so if we were to work out the gradient at the point x equals 4, we do the process again. That would be 4, 16. I choose a point that's close to it, so 4.1. Do 4.1 squared, find the gradient, and then 4.01, work out the y-coordinate, find the gradient. 4.001, so you can see exactly the same process repeated all over again. Do you know what answer we would get? What the answer would be getting closer and closer towards? I'll tell you what, I'm about to write down the answer, but before I do, if you're not sure, pause the video, work it out, okay? I hope you've done that because I'm about to reveal the answer, okay? So the answer turns out to be 8. Okay, did you get that? Great. Did you predict that? Even better, okay? Let's try it with x coordinate 5. Okay, again, if you're not too sure, if you can't see what the pattern is, do it, pause the video. Otherwise, just think about what it is and just wait for me to say, which is now, okay? 10, all right? Can you see what's going on? Can you see what's going on? We're looking for, how do we get from all of these numbers on the left to all these numbers on the right, okay? It's quite simple. We're just doubling the numbers, okay? So for a general x coordinate x, we're just doubling the numbers, 2x, okay? That is wonderful. Why is that wonderful, okay? It's wonderful for this reason, okay? For the whole graph, for the whole quadratic graph, and I'm not just talking about the positive integers now, I'm talking about the entire parabola, okay? Let's just try and draw a nice one, okay? Because you can check it works with negative values as well if you want, and it does, okay? For the entire parabola, y equals x squared, the gradient at any particular point is always going to be 2x, okay? The gradient is always 2x, because we double the x coordinate, which is absolutely amazing, because this is a very common curve. I'm sure you've dealt with parabolas quite a lot. It's an amazing fact that the gradient at any point you choose in this curve is going to be double whatever the x coordinate is, okay? And that's the beginnings of differentiation, okay? So it took us a little while to get there, okay? But that short amount of work has given us now our quick method of being able to work out the gradient at any point, okay? So what I could do is, I could just choose a point we've not even looked at that lies on the graph. Let's just choose the coordinate point, say, I don't know, 12, 144, because it lies on the point somewhere up there, okay? Can you work out the gradient at that particular point is going to be? Of course you can, it's just 24. See how quick and simple that was? We just look at the x coordinate, okay? I'll do another one, okay? What about the point -7, 49? That lies on the graph, -7 squared being 49. Can you work out the gradient for me at that point? Of course you can. It's just double the x coordinate. It'll be -14, okay? So this lovely simple rule has really helped to speed things up for us, okay? So that's kind of the end of part 1, okay? Part 2 is coming up next, and when I edit this, I'll decide whether to pause the video, do a fade out, or whether I should just sort of keep on going, okay? So I'll do the smile, just in case. Or if I just keep on the video going, then that's just a bit of a waste of time. Well, what's the next step? Okay, what's the next step? Well, the next step is, let's look at another graph. Let's look at another graph. And I'm going to draw this graph out, and you thinking it's the same, but actually no, it's y equals x cubed, okay? And of course the graph y equals x cubed looks like this, doesn't it? Okay, that's the whole graph, but I'm just interested in this bit here, okay? We're going to do the same process all over again, but with the graph y equals x cubed. So we choose a point there, okay? I'm going to call it coordinate 2, 8, because 2 cubed is 8. And I'm going to try and find what the gradient at the point 2, 8 is going to be. Okay, I'm going to go through the whole process all over again. So if you want, you pause the video and see if you can have a go at what I'm about to show you, okay? Or if not, you just keep on watching, and then when you feel comfortable, you pause it and then off you go. Or you just keep on watching, which is basically what a lot of people are probably going to do. So I'm going to choose a point that lies close to it, so 2.1, and then we're going to cube that, aren't we, to find the y coordinate. So 2.1 power of 3, okay, it gives me 9.261, and we're going to work out the gradient of the chord that joins these 2 points together. Okay, oh, it wasn't really a great straight line, was it? But you know it's meant to be a straight line. So the gradient AB1 is equal to that, subtract that. So that's going to be what, 1.261 divided by that, subtract that, 0.1, and the gradient there is going to be 12.61. Okay. Right, then we'll do the same again with another point, call that B2, and I'm just rubbing it off to make some space. That'll be even closer, 2.01. Then we've got to work out 2.01 cubed. Okay, whoops, try that again, 2.01, power 3, and that's 8.120601. Right, and then work out the gradient of that chord, AB2. So, yeah, this is just a generic sketch, of course. You can see the whole chords thing is going to get closer and closer to the gradient of the tangent as we get closer and closer. So it works for any of the graphs I'm drawing here. So that's going to be that, subtract that, which is going to be what, 0.120601 divided by difference between those, 0.01. So that divided by that is 12.0601. Can you guess yet what the number's heading towards? Well, if you can, well done. Just in case you can't, remember I'm doing this for the younger students as well. I did say maybe you're in year 8 or year 9. Year 8's maybe a little bit young. Okay, but year 9 is like on the cusp of being able to do this. Okay, you've got to have done some work with gradients really, and you have to understand what's going on here. So 2.001. Okay, can you predict what it's going to be when I do that to the power 3? Okay, 8.01206. Sorry, 0.006.001. Okay, yeah, similar sort of pattern exists in there, isn't there? Okay, and then gradient of AB3 is equal to that, subtract that, 8, whoa, no it's not, silly, let's try again, that, subtract that is 0.012006001 divided by that, subtract that, 0.001, which is going to be equal to 12.006.001. Can you now see what the gradient is heading towards? So we had that, then that. What's the number getting closer and closer towards? Yes, it's 12. Okay, it's 12. So that means that as the chord gets closer to that point, we say that when the chord and the gradient exist at the same point there, so the chord and the tangent exist at the same point there, then the gradients are equal. Okay, so it's going to be 12. Okay, so what I'm going to do is I'm just going to change this board and have it as the x cubed board, okay? And we're going to write down what's going on there, okay? So for y equals x cubed, we found the gradient at the point when x is 2, there is 12, okay? What happens next? We do exactly the same all over again, okay? So we'll work out what happens when x is 3. Now if you want, you pause the video and have a go yourself. I'm just going to get straight to the chase and tell you what the number is, okay? But it's the same process all over again, okay? I'm going to tell you that the number is 27. Maybe you pause the video and you got that. If you didn't, do it again. Okay. If you want to do it, you can do it, but otherwise just go with it for the moment. And then the next point will be 4. Okay. And the gradient there will be 48. And I'll give you just one more, because then you've got enough to be able to see what the pattern might be. So 5. Okay. And then you just work through the whole thing again. When the x coordinate is 5, the gradient there is going to be 75. Now, the question is, can you work out this time what's going on from these numbers to those numbers? There is something special that's linking these numbers to those numbers there. Can you work it out? Can you? Maybe pause the video, give yourself 5 minutes. Maybe you're going to have a cup of tea or something, or you're going to have your dinner and then think about it while you're doing that, while pretending to listen to the family conversation. Okay. Right, did you get it? Excellent. I'm hoping that you got. The rule is you do 3x squared, which means you square the x coordinate multiplied by 3. Let's check it. So that squared is 4, multiplied by 3 is 12. That squared is 9, multiplied by 3, 27. That squared is 16, multiplied by 3, 48. That squared 25, multiplied by 3, 75. Okay, so the x coordinate squared multiplied by 3. And that's the same for any point on the graph y equals x cubed. Okay, which is very, very handy. Now, we can do the same again with y equals x to the power 4, and x to the power 5, and x to the power 6, and just keep on going. If that's something you want to do, great, go ahead and do it. I'm not going to do that in this video, I'm just going to speed it along a little bit. Okay. On the other side of my board, I've just rubbed a little bit off already. Okay. I'm going to write down a different sort of table. Okay. I'm going to write down a table of what we've got so far and what the gradient for the points on those curves actually are. Okay. So far we've done the graph y equals x squared. That is a function, and we often use f of x notation. Okay, f of x equals x squared, same as y equals x squared, of course. And the gradient at any point, we use the notation f dash x or f prime x. Okay, and the gradient of that was 2x. Okay, so I'm just going to fill out this board here, and the graph we've just looked at, x cubed, we've got this here that is sometimes called the gradient function. Okay, 3x squared. The next one to go for will be x to the power of 4. Okay. Now either you've paused the video as I suggested and you've gone ahead and worked it out, or you're predicting what it's going to be. Okay. And it is 4x cubed. Okay. If you got that right, well done. If you predicted it, really good. Okay. And the next thing you do is x to the power of 5. Can you predict what it's going to be? Nice one. It is 5x to the power of 4. And then last one, the generic x to the power of n, where n here is, well, you can use an integer if you wish, but actually it works for fractions as well, rational numbers, it works for negative values and negative integers too. In fact, it works for real numbers. Okay, it is nx to the power of n minus 1. Okay, and that is our general result. Okay, while I'm rubbing the board, keep trying to have a think about why that actually is. Maybe this bit of science has given you some thinking time, but to be honest, if you really need some silent thinking time, I'm hoping you do the sensible thing and just pause the video, because then it's absolutely silent for you, isn't it? Okay. So what's going on then? Okay. Well, let me just write it out like this. We've got f of x is equal to x to the power of n, and then we say the gradient function, sometimes written like this, f with a dash there, x is equal to n, x to the n minus 1. The simple rule is that you bring the power down, make it the coefficient, so the n goes in front of the x, so you can see there it is, and you decrease the power by 1. And you can check with all of these, that's what's happening, okay? So here, the 3, put it in front, so it makes that, 3 there, and decrease the power by 1, so you get squared. This one there, the 4, put it in front, okay, and decrease the power by 1. So as another example, if you had f of x is equal to x to the power of 7, so what would the gradient function be? Yes, you put the 7 in front and you decrease the power by 1, 7x to the power of 6. Okay, that is what we call differentiation. Okay, and that is a standard differentiation result. And notice I've started already to use the standard notation we use, the fx and f dash x notation. Okay. That's not the most common notation, has to be said, particularly with A-level mathematics. The most common notation is this, okay? Because often when you're doing graphical work, you've got variables x and y, haven't you? Because you're drawing them on graphs, and so you use x coordinates, y coordinates, and you might have the equations y equals x to the power of n. Okay? If you're using y equals x to the power of n, then the common notation is this, dy dx. Okay? And then that's just the same result. So you've got two standard notations that you have to be aware of and you need to be able to use. Okay, so commonly when the function is given as f of x equals something, use the f notation, but when it's given in terms of y, use the y dy dx notation. Why dy dx? Well, in a nutshell, basically, okay, when you've got the gradient between 2 points there and there, just join them with a straight line like I did with all the chords. Okay, what do you do to find the gradient? You find the change in y over the change in x. Okay, we can represent that symbol there, which is a small delta, to represent a change in y, and that symbol there, delta, to represent a small change in x. And when you write down the gradient, okay, let's just put in the right angle there, then you'd say the gradient is the change in y over the change in x. Okay, not going to go into detail about it now. Okay, but the delta y we write as dy. And the delta x write as dx. That's really very basically, okay, why dy dx. I've skipped a lot of it out. If you want to know, just look up differentiation from first principles with limits and so on. But to be honest, if you're not in A level yet, that's going to really confuse you. Okay, and I wanted to keep it at a sort of lower level. Okay, so that's kind of really what differentiation is all about. Okay, now I'm going to stop it there because it's probably a lot to take in. The key points to remember from all of this is basically those. There's more to it than that, of course, but that's why I'm doing several different videos. Okay, my next video will show you, well, where do we go from here? Okay, but I'm hoping that you certainly got something out of this video. Okay, thanks for watching, and I'll see you again.